So we started off on Monday talking about exponential formulas, right? Exponential functions. From there, yesterday we talked about this compound interest formula. It tweaks the formula a little bit. Today we're going to tweak it a little bit more and come up with another formula known as the continuous growth formula. And what we learned as we did this was that the more often something is compounded, the more the output is. You get more and more if it's compounded more often. That was from yesterday. All right, so suppose you invest $1 at a rate of 100%. So $1, right, at a rate of 100%. So what's my R value whenever my percent is 100? 1. I heard someone say it earlier. I just wanted to get a few more people on board. I think it's 1. If you move the decimal over twice, you get 1. So it's going to be 1. So 100% is 1 as a decimal. And then how many times am I compounding it here? 1 time. And we're only doing this for 1 year, so it's 1 times 1, right? Now, this is pretty easy to do mentally. This is 1 plus 1, which is, and 2 to the first power is times 1. And, all right, so that's 2. All right, so basically at the end of the year, I would have $2. Now, quarterly, I'm still investing $1. We're still getting 100% interest rate, but this time it's being broken up into 4 chunks. So that's 4 times per year, right? Now I worked this one out earlier. It's not as easy to do mentally, but you end up with 2.44 something, and that makes sense because we saw that the more pieces you break it up into, the more you get, right? Now I'm not going to do the rest of these, but what I want to illustrate to you guys, and it seems kind of like stupid and pointless, but there's a reason for it, is what happens as your n value approaches bigger and bigger values. In other words, as n approaches infinity. Okay? So I'm going to compound it monthly, daily, hourly. That's how many hours are in a year. And then every minute. That's how many minutes are in a year. 525,600. Right? I have it. I've got the gift. So now I'm not going to work them out anymore. I got smart from last block where I had them do all the work, and that just took too long. So I just did it all, and here's the answer. So, but what I want you guys to notice that as you continue to increase that value of n, 2 things are happening. First of all, as we would expect, it's getting bigger every time. But something else that's happening is that it's reaching a limit. Do you guys see how it's increasing slower over time? Like from here to here is an increase in 40 cents. But from here to here, it's only like an increase of almost like 20 cents, right? So it increased slower. And from here to here, it's only 10 cents more. And then from here to here, it's arguably a penny more, if you want to round to the nearest penny. So it is still going up, but much slower over time. And so that means it's approaching a limit. It's reaching a value as n gets bigger and bigger and bigger into infinity. That value that's reaching, this is a really close approximation to it, is a very special number in mathematics called Euler's number. Okay? I'm going to let you guys watch a video about what Euler's number is, and then we'll talk a little bit more about it. But it's what happens when you take that compound interest formula and you compound it more and more and more. And as you let it be compounded more and more and more, basically it gets so small that we say it never stops compounding. It's compounding continuously. And that's going to give you the maximum possible output that you could possibly get with that particular rate. So let's see here. I'm going to pause my. So there's his value. This is how we get it. Something that I think is worth noting is the following thing. So on this slide, we might want to add a couple of things. So Notice that you can change, like I said, in calculus, they like to change numbers into E, okay? So in calculus, if I wanted to find the area under a curve for 9 to the x power, well, that's going to be a pain in the butt. But if you change it to that instead, if you rewrite 9 as E, it all of a sudden becomes easier. Okay, so that's one thing. Now, another thing is that notice that anytime this number is positive, this number here will be greater than 1. Anytime this number is negative, that number is less than 1. Now, when we're if I was talking about this 9 to the x power, is that a growing function or a decaying function?
Growing.
Why is it growing?
Positive.
Yes and no.
It's bigger than 1.
There you go. That's the one I'm looking for. It's bigger than 1. So this is growing. It's an increasing one, right? But this one would be decaying, right? Because it's less than 1.7. Okay. Now, if we rewrite these with e's, it's a good question. You don't need to write this, but I will tell you what to write in just a second. If I rewrote these as e's instead, we have a new fact, and this is the fact that I'll have you write down in just a second, is that if the power, if your r value here, the constant up here, the exponent, is positive, then it's increasing. If it's negative, it's decreasing. So that would be something that we want to write, but we won't write it yet. I'll show you where we can write that in a minute. So what we did was we took our compound interest formula and we let n approach infinity. And really we just did it to this piece here because I made everything else equal 1, so they kind of made them negligent. And that little piece there just became E, didn't it? So our compound interest formula becomes PERT. Okay, you can call it PERT if you want to. And what that is, that's called continuous compounding. You're breaking it up into infinitely small chunks, and you're adding that percentage infinitely many times. And what that does, it gives you the maximum possible output. Okay? Besides the fact that it's also very useful in calculus. So E matters, it's important. So here it is. If an initial deposit is compounded continuously, the key word here is continuously, at an annual rate of R, the balance T years later can be calculated using this formula. And this is where we'll add our little note, okay? If R is positive, it's increasing. If R is negative, it's decreasing. So that means if R is positive, it goes up. If R is negative, it goes down. That's interesting. It's not on mine. Okay, so we're going to do a couple of examples here, and then some practice, and that'll be it. It's not too bad. It's a lot like what we did yesterday. You're going to need to know how to do the calculator again, though. So if you want to take a moment, come grab a calculator. Now would be the time. So first thing I want you guys to know is we've learned 3 formulas at this point. Okay, this is at the bottom of your notes that I printed for you. We've learned 3 formulas. We've had the regular exponential formula. We have the compound interest formula, and you know you're going to use that anytime they're talking about compound interest. This one, your keyword you're looking for is the word continuous. If you see the word continuous, that means it's growing continuously. Okay, so it's not like the regular compound where it only happens at the end of the first quarter and then at the end of the second, at the end of the third. It's just constantly growing. Okay, so let's go ahead and jump back here to example 2. It says, suppose you invested $1,500 into an account with an APR, which is short for annual percentage rate, of 10% compounding continuously. How much would there be after 1.5 years? So the key word here is compounded continuously. That indicates to us that we're using this. Okay, this is still the output, the final amount. This is still the starting amount. This is still our percent, and this is still the number of years. So the variables don't really change their meaning, but what is important is you guys understand that E is not a variable, it's a number. Okay, it's 2.71 something, right? So let's go ahead and plug these in. Where am I going to put the 1500 at?
What you input like 7-1.
No, I'll tell you how to deal with that in a second. But for now, where does the 1500 go? P. Then we're going to put E. And what's my R value? 0.1, right? Don't forget to change it to a decimal. And how many years? Now we got to know how to put this into our calculator, you guys. So get your calculators ready for me. To figure this out on the calculator, you're going to start by typing 1500. Then you're going to put the E in there. Now you can't just push, the E is like hidden. It's hidden behind the LN button. So what we have to do is we have to push the button second, and then you're going to push the button LN, because that's how you access E. So push second and then LN. After that, you're going to see that little caret symbol with some parentheses on it. And inside of those parentheses, you're going to type our exponent part. So 0.1 times 1.5. And from there, you should be able just to push equal and get your answer. So by doing that, let's see what we get. What'd you get? Am I still working on mine?
1742.7.
Cool. And what this is that if a bank was really giving you 10% interest for 1.5 years on $1,500, this is the best possible amount you could get. It would be better than being compounded quarterly, monthly, daily, even by the minute. That's the best possible output you could get. So continuous compounding is the best. All right? Any questions about that one?
This is the formula that we use to solve continuous compound.
Yeah. Now the word compound doesn't have to be there, but the word, if you see the word continuously growing or something like that, that's an E formula. All right. Let's proceed to another example. Go ahead and read that and see if you guys can fill in the formula. Don't get the final answer yet, but fill in the formula. There's a little twist here. See if you can figure it out. Okay. Okay. Let's see what you guys have gotten here. Vivian, what did you get?
The answer?
Just the formula.
A equals 100 E.
Thank you. Okay.
And then, I don't know if it's negative.
That was the twist. It is.
Negative 0.17 and then 8 hours.
Good. So the twist is that our R is negative. Why is the R negative?
Because you're losing.
It's decaying, right? We're losing the amount of caffeine in our bloodstream. So it's R in this problem is going to be negative 0.17 since it's decreasing. Now, here's another thing that's good about continuous, right? When you're talking about banking, it makes sense. Like, okay, at the end of the quarter, they'll give you that percent. right? At the end of the next quarter, they'll give you that percent, and so on, right? But when you're talking about caffeine being metabolized out of your system, does your body sit there and wait, okay, an hour's gone by, I gotta get rid of 17 right now? It doesn't work that way, does it? What's happening is, by the end of an hour, 17% is gone, because it's continuously taking it away. So, another example of why continuous growth actually just makes a lot more sense than regular compounding. Okay, so let's go ahead and work out. So go ahead and see if you could type it in your calculator now and get a final answer. So we had the question, will the answer be negative? The answer is no. Negative exponents don't make the answer negative. Negative exponents make it a reciprocal, so they make it smaller. Okay, so it makes it decrease, but it won't be negative. All right, so Cassandra, yes. What did you get? Yeah. And that's milligrams, right? So that's continuous growth. So why do we care about continuous growth? Because heck of a lot easier in calculus to work with. Second of all, real life scenarios don't always just decrease or increase at sporadic moments in time. They constantly increase and decrease. So this is a much better fit for a lot of growth questions and decay questions that are exponential. So here's a couple of problems for you guys. Go ahead and knock those out.